Welcome back. This is the second segment for our lecture on section 5.2. You'll recall last time we talked about things from a conceptual manner, sort of good practices for proof techniques in general, but more specifically related to proving trigonometric identities. What I'm going to do in this segment is I'm going to actually prove a couple things. Understand that there's more than one way to skin a cat, as I like to say. You can obviously use different techniques to prove any specific identity, and that is one of the actual intriguing things about mathematics is there's no one right way to do it. I'm going to try to be as formal as I can, and hopefully you can model that behavior in your own work. But I want to just basically say here while I'm switching over to my document camera, from a very general standpoint, it is simply not the case that there is one way to do this. There is no set procedure for doing proofs. It requires experimentation to develop the necessary skills, and often you will you'll realize that you've kind of gone down the wrong path, or you have to start and stop frequently. It's just the nature of the beast. These can take a long period of time to do an individual problem that it may take another person a very, very short period of time, because it's more like solving a puzzle than building something out of Legos or whatever. Maybe that analogy doesn't make much sense, but anyways, okay. So here we are in section 5.2. I believe we're now on page 4 of the running total. Okay, so here's an example of the kind of problem you might see. I'll just start with example 1 here. Show that, which is a clever way of saying prove. Show that secant of x times the quantity sine of x plus cosine of x is equal to 1 plus tangent of x. Okay? So here's where we have to employ some of those techniques. Remember I said pick one side. Pick the more complicated side. Start there and start doing things to that using fundamental identities. So hopefully it's pretty clear that the left-hand side of this is the quote more complicated side, right? So I'm gonna start. I think that one's pretty obvious. Sometimes they're not so obvious. So I'm going to start here with the left-hand side. So this is the formal beginning of my proof. I will start by writing the original expression for the left-hand side. So secant of x times the quantity sine of x plus cosine of x. And my first step here, typically there's a couple different things I could do. The order is not necessarily important, but you may recall, I mean, this is the first one, so maybe we should employ some of the strategies that we've done before, where maybe say, I don't know, you've got 3 different types of functions here. Maybe we can get it down to 2 by making a substitution for secant so that it's a version of sine and cosine. And so I'll do that first. So since my space isn't quite as big as I'd like, I'm going to kind of jump down to the next line here to start my equals. So you have the statement, the original statement of the left-hand side. It could start with the right-hand side, but we started with the left. And then this will be connected by a series of equal signs until we end up with 1 plus tangent of x at the bottom. So, and we'll keep a running total of our rationale over here to the right. So the first thing I'm going to do is I'm going to make the substitution for secant. And secant is equal to the reciprocal of cosine. So I will write it like so. And my rationale for this, well, that's a reciprocal identity, right? Okay. The next step is an algebraic step. I'm just going to, and I could have done the algebra first, but usually when you see something inside of a parentheses like this, you did this in algebra too, algebra as well, where you simply, the first thing you should be thinking about doing is distributing, right? Just distribute that stuff through so that you don't have things all in a factored, bunched up manner. So that's what I'm going to do next, is I'll distribute. And so I have 1 over cosine times sine, which is just simply sine of x over cosine of x. Then plus 1 over cosine times positive cosine. So that'll be cosine of x over cosine of x. And that is just simply an algebraic step, right? I mean, that's how the distributive property works in some sense. So the next step, we have some choices, but for me, I'd say the next step, I want to clean up the algebra as much as possible. So I'm gonna do this cancellation right here. This is obviously the number 1. So I've got sine of x over cosine of x plus 1. This is, again, an algebraic step. And finally, hopefully everybody is seeing it, this is tangent, right? Sine of x over cosine of x is tangent of x by a quotient identity. And so I'll go ahead and make that my next step. Right, we've got equal to tangent of x plus 1 by a quotient identity. So now the question is, are we done? Well, technically, we started with the left-hand side is we started with the left-hand side. We should end with the right-hand side. Now, to your eyes, because you're used to the way algebra functions, 1 plus tangent of x is the same thing as tangent of x plus 1. That's not universally true in all algebraic systems. It is true of the field of real numbers, and so I feel like this is kind of where we can stop, because we all recognize that the commutative property holds for addition. But if you wanted to be thoroughly anal about this, you would say then that this is equal to 1 plus tangent of x, and again, this is an algebraic process, okay? Am I gonna count you off for it? No, obviously not, because this isn't an algebra class. What I'm more interested in is that all of the trigonometry, which only really occurs here and here, is executed properly, and that you don't make some kind of very obvious algebraic mistake along the way. Right, so that's kind of the basis of what a typical problem will look like. Okay, so let me I'm pretty much out of paper here. Let me do another one. So again, this is section 5.2. I think we're now on page 5. Okay, so same sort of setup. I'm going to start with this. So show that. This one will be a little bit similar to the last one. These aren't actually very challenging. They do get harder, trust me. So we're wanting to show that cotangent squared of x times the quantity tangent squared of x plus 1 is equal to cosecant squared of x, which is kind of interesting. Hopefully you can, because a lot of these are sort of, you're taking visual cues from the expressions themselves. As soon as I see this, I'm looking at that going, hey, that's a Pythagorean identity. Right? That's kind of how my thought process is working. But, to go back to kind of the suggestions we had, which is that first start with the more complicated side, I think it's very, very clear that the left-hand side is more complicated. So I will start, again, this is kind of where my proof begins. Cotangent squared of x times tangent squared of x plus 1 is equal to, well, I'm not going to have enough space here. So you can do one of two things first. You can either try to distribute things through, which seems kind of silly, or you can make that substitution I was talking about right off the bat, which is what I'm going to do, okay? So remember, And I'm going to kind of be real meticulous with my parentheses here. So cotangent squared of x times, and tangent squared of x plus 1 is equal to secant squared of x. And that is by a Pythagorean identity, the so-called second Pythagorean identity. Okay, so there's so far so good. I think the next step, we can do this in 2 steps at this point. If you're proficient with the fundamental identities, the next step would be simply to substitute what cotangent is in terms of a quotient identity. It is cosecant over secant, so cotangent squared will be cosecant squared over secant squared. You may not recognize that. And you may actually decide, well, I don't really know, I don't have a whole lot of familiarity working with these trig functions, so let me turn them all into sines and cosines, and then see what happens there. So let me sort of show you the hard way, and then I will back up and I'll show you where you could have taken a shortcut. All right. So again, let's assume that I'm not real proficient with all of the fundamental identities. And what would I do? I go, well, I'm not really sure how to proceed. Maybe I just turn everything into sine and cosine and see what happens. So the next substitution would be, all right, well, let's turn cotangent into sine and cosine. So that'll be cosine squared x over sine squared of x. And then maybe do the same thing with secant squared by the reciprocal identity. One of the reciprocal identities, that'd be 1 over cosine squared of x. So again, I'm kind of doing 2 different classes of identities at the same time. So I'm going to go ahead and say RQ, right, for reciprocal and quotient. And then I've got some algebraic cancellation. Notice I've got a cosine squared in the numerator, cosine squared in the denominator. What's that leave me with? Well, that's 1 over sine squared of x. That's an algebraic process, okay? And then finally, hopefully everybody recognizes 1 over sine squared is in fact cosecant squared. And that again, that is another reciprocal identity, okay? And let's make sure we started with the left and ended with the right, okay? So this is a concise proof. Now, the thing is, and this is sort of where the subtlety comes in, is that I spent 2 extra steps to do this. What I could have done instead is, instead of this line and then proceeding, if I instead had used a different quotient identity, my next step would have been to say, well, cotangent squared, well, that's equal to cosecant squared over secant squared. And then I'm multiplying this by secant squared. This is now a reciprocal identity, right? And the cancellation is obvious, right? We have secant squared in a denominator, secant squared in a numerator. The net result is cosecant squared of x. And this proof is done, right? This is just an algebraic process. Okay, so what did we do there? Well, we saved about 2 steps. Maybe only 1, but it is more efficient. However, either way is right. So I don't want anybody to get to feel like there's only one way to do things. Okay, so let me, I'll have those notes out there on Blackboard so you can review those at your leisure. I'm going to try to do 1 more, and then I'm probably going to end this segment. Well, I don't know, maybe I'll make this one a little bit longer than normal, just so I can get the 4 that I intended to use. Okay, so let me start with one. So this is now page 6. Okay, so let's start with prove. Those kind of terms are used interchangeably. Prove, show that. Prove that tangent squared of, let's use a different letter this time. How about S? Tangent squared of S over secant squared of s, show that, or I'm sorry, s, prove that this expression is equal to 1 plus cosine of s. I've already made this ridiculous. Let me just start all over here. I'm running out of space. I'm not used to such a large marker. So section 5.2, page 6, example 3. Prove that the expression tangent squared of s over secant squared of s is equal to the product 1 plus cosine of s times 1 minus cosine of s. Okay, so now maybe a little bit less obvious which side is the more complicated side, so to speak, right? You've got on one side, you've got some division and two different trig functions that are maybe a little less familiar to you. On the right-hand side, we have this factored business over here. It's hard to say which one's actually more complex. It really, if they both are pretty much equally complex, then it really doesn't matter which side you work from. But here's what my thinking is. I'm familiar with sine and cosine, right? That's how I think about this. I'm familiar with sine and cosine, and if I start on this side, my first step would be to turn things into sines and cosines. I already have kind of in my own mind what a first step would be. If I start here, I don't necessarily know where to go from here, other than to just distribute this stuff out and hope that I find some interesting, you know, some sort of an interesting fundamental identity I can use. So that's my thinking. Less familiar trig functions, basically the same level of complexity in terms of like if I had to calculate a value. So let me start with the left-hand side, and I think you'll see that this gets pretty slick. So starting with tangent squared of s over secant squared of s, okay? This is going to be equal. Now, like I said, what I'm going to do first is I'm going to use reciprocal and quotient identities to turn this into just some combination of sine and cosine. So tangent squared of s, that's going to be sine squared of s over cosine squared of s. And then, of course, secant squared is 1 over cosine squared, cosine, 1 over cosine squared of s. This is a combination of reciprocal and quotient identities. Okay. Now, I'm looking at a complex fraction here. There's a fraction in the numerator, a fraction in the denominator. They both happen to have the same denominator, and so that's actually going to go away. The very next step here is to say, well, this happens to be equal to just sine squared. Nice. So it's like, okay, well, where do I go from here? By the way, that's just an algebraic process. So, all right, you know, usually when we're working with these identities, we try to boil down a complex side into a less complex side. It's easy to simplify. I think if you think back about your experiences in algebra, you probably never had a situation where somebody asked you, people certainly asked you to simplify expressions, but I don't know how many times people ask you to complexify an expression. It just doesn't really happen. But we're going to have to complexify this to be able to get that thing on the right, because this is, if we were trying to prove that this is equal to that, we would definitely start with this side. I hope that's clear. So in some cases, it maybe makes sense to kind of stop in the middle and then restart the proof where this is your new target. But I'm not going to do that. I'm going to show you a little trick. Anytime you see these sort of squared trig functions, it sometimes makes sense to try to use a Pythagorean identity to kind of get yourself out of a mess. So remember, from the first Pythagorean identity, sine squared plus cosine squared is equal to 1. So what does that say about sine squared? Well, sine squared then has to be 1 minus cosine squared of s, which is Pythagorean identity. Okay, now this is where we're complexifying, so to speak. Okay, well now notice this is a difference of squares, right? This is 1 squared minus cosine squared. And remember back that discussion about factoring, that, let's try factoring. I mean, the right-hand side is in a factored form, so at some point we're going to have to factor something, and this might be the right thing to do, which in fact it is. Remember, this is sort of a squared minus b squared is equal to a plus b, which b in this case is cosine of s, times a minus b, and that is an algebraic step, right? And that is the target. That's exactly what we wanted to end with. So let's review. We started with the left-hand side, a series of justified steps. This one was kind of the weird one, that transition right there, but you'll do this enough that hopefully this will become a little familiar. We end up with the right-hand side. So this proof is done. Okay, so I'm looking at the time, and here's what I'm going to do, folks. I'm gonna pause this. I'm going to actually finish this video here, but I will pick this up. I do have some more examples. I think the next one actually will take some time, so I'll be back in segment 3.